is the softmax activation function, then the output will be this. It's basically taking that temporary variable t and normalizing it to sum to 1. So this then becomes A of L. So you notice that in the z vector, the biggest element was 5, and the biggest probability ends up being this first probability. The name softmax comes from contrasting it to what's called a hard max, which would have taken the vector z and collapsed it to this vector. So hard max function will look at the elements of z and just put a 1 in the position of the biggest element of z, and then zeros everywhere else. And so this is a very hard max, where the biggest element gets an output of 1 and everything else gets an output of 0. Whereas in contrast, the softmax is a more gentle mapping from z to these probabilities. So I'm not sure if this is a great name, but at least that was the intuition behind why we call it a softmax. Is in contrast to the hard max. And one thing I didn't really show, but had alluded to, is that softmax regression, or the softmax activation function, generalizes the logistic activation function to C classes rather than just 2 classes. And it turns out that if C is equal to 2, then softmax with C equals to 2 essentially reduces to logistic regression. And I'm not going to prove this in this video, but the rough outline for the proof is that if C equals to 2 and if you apply softmax, then the output layer, AL, will output 2 numbers if C equals 2. So maybe it is 842 and 158, right? And these 2 numbers always have to sum to 1. And because these 2 numbers always have to sum to 1, they're actually redundant, and maybe you don't need to bother to compute 2 of them, maybe just need to compute 1 of them. And it turns out that the way you end up computing that number reduces to the way that logistic regression is computing its single output. So that wasn't much of a proof, but the takeaway from this is that softmax regression is a generalization of logistic regression to more than 2 classes. Now let's look at how you would actually train a neural network with a softmax output layer. So in particular, let's define the loss function you use to train your neural network. Let's take an example. Let's say you have an example of a training set So the example from the previous video means that this is an image of a cat because it falls into class 1. And now let's say that your neural network is currently outputting y hat equals, so y hat will be a vector probability scale sum to 1, 4.1, 4.4. So you can check that sums to 1, and this is going to be a L. So the neural network is not doing very well in this example because this is actually a cat and assigned only a 20% chance that this is a cat. So it didn't do very well in this example. So what's the loss function you want to use to train this neural network? In softmax classification, the loss we typically use is negative sum of j equals 1 through 4, and it's really sum from 1 to c in the general case, so I just use 4 here, of y log yj log y hat of j. So let's look at our single example of to better understand what happens. Notice that in this example, y1 equals y3 equals y4 equals 0 because those are zeros and only y2 is equal to 1. So if you look at this summation, all the terms with 0 values of yj will equal to 0, and the only term you're left with is negative y2 log y hat 2, because when you sum over the indices of j, all the terms will end up 0 except when j is equal to 2. And because y2 is equal to 1, this is just negative log y hat 2. So what this means is that if your learning algorithm is trying to make this small, because you use gradient descent to try to reduce the loss on your training set, then the only way to make this small is to make this small, and the only way to do that is to make y hat 2 as big as possible. And these are probabilities, so it can never be bigger than 1, but this kind of makes sense because if x for this example is a picture of a cat, then you want that output probability to be as big as possible. So more generally, what this loss function does is it looks at whatever is the ground truth clause in your training set, and it tries to make the corresponding probability of that clause as high as possible. If you're familiar with maximum likelihood estimation in statistics, this turns out to be a form of maximum likelihood estimation. But if you don't know what that means, don't worry about it. The intuition we just talked about will suffice. Now, this is the loss on a single training example. How about the cost, J, on the entire training set? So the cost of the setting of the parameters, and so on, of all the weights and biases, you define that as pretty much what you guess, sum of the entire training set of the loss, your learning algorithms predictions, summed over your training examples. And so what you do is use gradient descent in order to try to minimize this cost. Finally, one more implementational detail. Notice that because C is equal to 4, Y is a 4 by 1 vector, and Y hat is also a 4 by 1 vector. So if you're using a vectorizing notation, the matrix capital Y is going to be Y1, Y2 through Ym stacked horizontally. And so, for example, if this example up here is your first training example, then the first column of this matrix Y will be 0, 1, 0, 0, and then your second example, maybe the second example is a dog, maybe the third example is none of the above, and so on. And then this matrix capital Y will end up being a 4 by n dimensional matrix. And similarly, Y hat will be Y hat 1 stacked up horizontally going through Y hat m. So this is actually Y hat 1 or the output on the first training example. Then Y hat will be this 0.3, 0.2, 0.1, 0.4, and so on. And Y hat itself will also be a 4 by n dimensional matrix. Finally, let's take a look at how you implement gradient descent when you have a softmax output layer. So this output layer will compute ZL, which is C by 1 in our example, 4 by 1, and then you apply the softmax activation function to get AL, or Y hat, and then that in turn allows you to compute the loss. So we've talked about how to implement the forward propagation step of the neural network to get this output and to compute that loss. How about the back propagation step, or gradient descent? Turns out that the key step, or the key equation you need to initialize backprop is this expression that the derivative with respect to z at the last layer, this turns out you can compute as y hat, the 4 by 1 vector, minus y, the 4 by 1 vector. So you notice that all of these are going to be 4 by 1 vectors when you have 4 classes, and c by 1 in the more general case. And so this, going by our usual definition of what is dz, this is a partial derivative of the cost function with respect to zl. If you're an expert in calculus, you can derive this yourself. Or if you're an expert in calculus, you can try to derive this yourself, but using this formula will also just work fine if you ever need to implement this from scratch. But with this, you can then compute dzl and then sort of start off the background process to compute all the derivatives you need throughout your neural network. But it turns out that in this week's programming exercise, we'll start to use one of the deep learning programming frameworks. And for those programming frameworks, usually it turns out you just need to focus on getting the forward prop right. And so long as you specify the programming framework, the forward prop pass, the programming framework will figure out how to do back prop, how to do the backward pass for you. So this expression is worth keeping in mind for if you ever need to implement softmax regression or softmax classification from scratch, although you won't actually need this in this week's programming exercise because the programming framework you use will take care of this derivative computation for you. So that's it for softmax classification. With it, you can now implement learning algorithms to categorize your inputs into not just one of 2 classes, but one of C different classes. Next, I want to show you some of the deep learning programming frameworks which can make you much more efficient in terms of implementing deep learning algorithms. Let's go on to the next video to discuss that. In the early days of deep learning, people used to worry a lot about the optimization algorithm getting stuck in bad local optima. But as the theory of deep learning has advanced, our understanding of local optima is also changing. Let me show you how we now think about local optima and problems of the optimization problem in deep learning. So this was a picture people used to have in mind when you worried about local optima. Maybe you're trying to optimize some set of parameters, we call them W1 and W2, and the height of the surface is the cost function. So in this picture, it looks like there are a lot of local optima, in all those places, and it'd be easy for gradient descent or one of the other algorithms to get stuck on a local optimum rather than find its way to a global optimum. It turns out that if you're plotting a figure like this in 2 dimensions, then it's easy to create plots like this with a lot of different local optima. And these very low dimensional plots used to guide our intuition. But this intuition isn't actually correct. It turns out if you create a neural network, most points of 0 gradients are not local optima, like points like this. Instead, most points of 0 gradient in the cost function are actually saddle points. So that's a point with a 0 gradient. Again, this is maybe W1, W2, and the height is the value of the cost function J. But informally, a function in a very high dimensional space, if the gradient is 0, then in each direction it can either be a convex light function or a concave light function. And if you're in, say, a 20,000 dimensional space, then for it to be a local optima, all 20,000 directions need to look like this. And so the chance of that happening is maybe very small, maybe 2 to the minus 20,000. Instead, you're much more likely to get some directions where the curve bends up, like so, as well as some directions where the curve function is bending down, rather than have them all bend upwards. So that's why in very high dimensional spaces, you're actually much more likely to run into a saddle point, like that shown on the right, than the local optimum. Oh, and as for why this surface is called a saddle point, if you can picture maybe this is a sort of saddle you put on a horse, right? So maybe if this is a horse, I guess there's a head of a horse, there's the eye of a horse, I guess, and right, well, not a great drawing of a horse, but you get the idea. Then you, the rider, would sit here in the saddle, so that's why this point here, where the derivative is 0, that point is called a saddle point. It's really the point on the saddle where you would sit, I guess, and that happens to have, derivative 0. And so one of the lessons we learn in history of deep learning is that a lot of our intuitions about low dimensional spaces, like what you can plot on the left, they really don't transfer to the very high dimensional spaces that our learning algorithms are operating over. Because if you have 20,000 parameters, then J is really a function over a 20,000 dimensional vector, and you're much more likely to see saddle points than local optima. If local optima aren't a problem, then what is a problem? It turns out that plateaus can really slow down learning. And a plateau is a region where the derivative is close to 0 for a long time. So if you're here, then gradient descent will move down the surface, and because the gradient is 0 or near 0, the surface is quite flat. You can actually take a very long time, to slowly find your way to maybe this point on the plateau, and then because of a random perturbation to the left or right, maybe then finally, I'm going to switch pen colors for clarity, your algorithm can then find its way off the plateau. But to take this very long, slow path before it's found its way here, and then could get off this plateau. So the takeaways from this video are, first, you're actually pretty unlikely to get stuck in bad local optima, so long as you're training a reasonably large neural network. So you have a lot of parameters, and the cost function J is defined over a relatively high dimensional space. But second, that plateaus are a problem, and they can actually make learning pretty slow. And this is where algorithms like momentum or RMS-prop or Adam can really help you learn the algorithm as well. And these are scenarios where more sophisticated optimization algorithms, such as Adam, can actually speed up the rate at which you could move down the plateau and then get off the plateau. So because neural networks are solving optimization problems over such high dimensional spaces, to be honest, I don't think anyone has great intuitions about what these spaces really look like, and our understanding of them is still evolving. But I hope this gives you some better intuition about the challenges that the optimization algorithms may face. So that, congratulations on coming to the end of this week's content. Please take a look at this week's quiz as well as the programming exercise. I hope you enjoy practicing some of these ideas with this week's programming exercise, and I look forward to seeing you at the start of next week's videos. Welcome to the last video for this week. There are many great deep learning programming frameworks. One of them is TensorFlow. I'm excited to help you start to learn to use TensorFlow. What I want to do in this video is show you the basic structure of a TensorFlow program and then leave you to practice, to learn more details and practice them yourself in this week's programming exercise. This week's programming exercise will take some time to do, so please be sure to leave some extra time to do it. As a motivating problem, let's say that you have some cost function j that you want to minimize. And for this example, I'm going to use this highly simple cost function j of w equals w squared minus 10w plus 25. So that's the cost function. You might notice that this function is actually w minus 5 squared. If you expand out this quadratic, you get the expression above. And so the value of w that minimizes this is w equals 5. But let's say we didn't know that, and you just have this function. Let's see how you can implement something in TensorFlow to minimize this. Because a very similar structure of program can be used to train neural networks, where you can have some complicated cost function j of wb depending on all the parameters of your neural network. And then similarly, you'll be able to use TensorFlow to automatically try to find values of w and b that minimize this cost function. But let's start with the simpler example on the left. So I'm running Python in my Jupyter notebook, and to start up TensorFlow, you import NumPy as NP, and it's idiomatic to use import TensorFlow as TF. Next, let me define the parameter w. So in TensorFlow, you're going to use tf.variable to define a parameter. Type equals tf.float 32. And then let's define the cost function. So remember, the cost function was w squared minus 10w plus 25. So we use tf.add. So we have w squared plus tf.multiply. So the second term was minus 10 times w. And then I'm going to add that to 25. So we put another tf.add over there. So that defines the cost j that we had. And then I'm going to write train equals tf.train.gradient descent optimizer. Let's use a learning rate of 0.01, and the goal is to minimize the cost. And finally, the following few lines are quite idiomatic. Init equals tf.global variables initializer, and then session equals tf.session. So this starts a TensorFlow session, session.run init to initialize global variables. And then for TensorFlow, to evaluate a variable, we're going to use ses.run w. We haven't done anything yet. So with in this line above, initialize w to 0 and define a cost function. We've defined train to be our learning algorithm, which uses a gradient descent optimizer to minimize the cost function. But we haven't actually run the learning algorithm yet. So session.run will evaluate w. Let me print session.run. So if you run that, it evaluates w to be equal to 0 because we haven't run anything yet. Now, let's do session.run train. So what this will do is run one step of gradient descent, and then let's evaluate the value of w after one step of gradient descent and print that. So we do that. After one step of gradient descent, w is now 0.1. Let's now run 1,000 iterations of gradient descent. So run train, and let's then print session.run w. So this will run 1,000 iterations of gradient descent, and at the end, W ends up being 4.99999. Remember, we said that we're minimizing W minus 5 squared, so the optimal value of W is 5, and it got very close to this. So hope this gives you a sense of the broad structure of a TensorFlow program. And as you do the programming exercise and play with more TensorFlow code yourself, some of these functions that I'm using here will become more familiar. Some things to notice about this: W is the parameter we're trying to optimize, so we're going to declare that as a variable. And notice that all we had to do was define a cost function using these add and multiply and so on functions. And TensorFlow knows automatically how to take derivatives with respect to the add and multiply, as well as other functions, which is why you only had to implement basically forward prop, and it could figure out how to do the back prop or the gradient computation, because that's already built in to the add and multiply as well as the squaring functions. And by the way, in case this notation seems really ugly, TensorFlow actually has overloaded the computation for the usual plus, minus, and so on. So you could also just write this nicer format for the cost, comment that out, and rerun this and get the same result. So once W is declared to be a TensorFlow variable, the squaring, multiplication, adding, and subtraction operations are overloaded, so you don't need to use this uglier syntax that I had above. Now, there's just one more feature of TensorFlow that I want to show you, which is this example minimized a fixed function of W. What if the function you want to minimize is a function of your training set? So what if you have some training data X, and when you're training a neural network, the training data X can change. So how do you get training data into a TensorFlow program? So I'm going to define Tx, which is, think of this as playing a role of training data, or really the training data with both X and Y, but we only have X in this example. So this is going to define X for placeholder, but we have training. So I'm going to define Tx, which is, think of this as playing a role of training data, or really the training data with both X and Y, but we only have X in this example. So this is going to define X for placeholder, and it's going to be of type float 32, and let's make this a 3x1 array. And what I'm going to do is, whereas the cost here had fixed coefficients in front of the three terms in this quadratic, it was 1 times W squared minus 10 times W plus 25. We could turn these numbers 1, minus 10, and 25 into data. So what I'm going to do is replace the cost with cost equals X 0, 0 times W squared plus X1, 0 times W plus X2, 0, times 1. So now X becomes sort of like data that controls the coefficients of this quadratic function. And this placeholder function tells TensorFlow that X is something that you provide the values for later. So let's define another array. Coefficients equals np dot array 1 minus 10, and yes, the loss value was 25. So that's going to be the data that we're going to plug into X. So finally, we need a way to get this array coefficients into the variable x. And the syntax to do that is, it is during the training step that the values for will need to be provided for x. So I'm going to set here feed dict equals x maps to coefficients. And I'm gonna change this. I'm gonna copy and paste, put that here as well. All right, hopefully I didn't have any syntax errors. Let's try rerunning this, and we get the same results, hopefully, as before. And now if you want to change the coefficients of this quadratic function, let's say you take this 10 and change it to 20 minus 20, and let's change this to 100. So this is now the function x minus 10 squared, and if I rerun this, hopefully I find that the value that minimizes x minus 10 squared is w equals 10. Let's see. Cool, great. And we got w very close to 10 after running 1,000 iterations of gradient descent. So what you see more of when you do the programming exercise is that a placeholder in TensorFlow is a variable whose value you assign later, and this is a convenient way to get your training data into the cost function. And the way you get your data into the cost function is with this syntax. When you're running a training iteration, to use the feed dict to set x to be equal to the coefficients here. And if you're doing mini-batch gradient descent, where on each iteration you need to plug in a different mini-batch, then on different iterations you use the feed dict to feed in different subsets of your training set, different mini-batches, into where your cost function is expecting to see data. So hopefully this gives you a sense of what TensorFlow can do. And the thing that makes it so powerful is all you need to do is specify how to compute the cost function. And then it takes derivatives, and it can apply a gradient optimizer, or an atom optimizer, or some other optimizer with just, pretty much 1 or 2 lines of code. So here's the code again. I've cleaned this up just a little bit. And in case some of these functions or variables seem a little bit mysterious to you still, they will become more familiar after you practice with it a couple times by working through the programming exercise. Just one last thing I want to mention. These 3 lines of code are quite idiomatic in TensorFlow. And what some programmers will do is use this alternative format, which basically does the same thing. Set session to tf.session to start the session, and then use the session to run init, and then use the session to evaluate, say, w, and then print a result. But this with construction is used in a number of TensorFlow programs as well. It more or less means the same thing as the thing on the left, but the with command in Python is a little bit better at cleaning up in case there's an error or an exception while executing this in a loop. So you see this in the programming exercise as well. So what is this code really doing? Let's focus on this equation. The heart of a TensorFlow program is something to compute a cost, and then TensorFlow automatically figures out the derivatives and how to minimize that cost. So what this equation, or what this line of code is doing, is allowing TensorFlow to construct a computation graph. And a computation graph does the following. It takes x0, 0, it takes w, and then I guess w gets squared, and then x0, 0 gets multiplied with w squared. So you have x0, 0 times w squared, and so on, right? And eventually, this gets built up to compute this x0, 0 times w squared plus x10 times w plus and so on. And so eventually you get the cost function, right? And I guess the last term to be added would be x20, right? Gets added to be the cost. I won't write out the formula for the cost. And the nice thing about TensorFlow is that by implementing basically forward propagation through this computation graph to compute the cost, TensorFlow has already built in all the necessary backward functions. So remember how training a deep neural network had a set of forward functions and a set of backward functions. And programming frameworks like TensorFlow have already built in the necessary backward functions, which is why by using the built-in functions to compute the forward function, it can automatically do the backward functions as well to implement backpropagation through even very complicated functions and compute derivatives for you. So that's why you don't need to explicitly implement backprop. And this is one of the things that makes the programming frameworks help you become really efficient. If you look at the TensorFlow documentation, I just want to point out that the TensorFlow documentation uses a slightly different notation than I did for drawing the computation graph. So it uses x00, w, and then rather than writing the value like w squared, the TensorFlow documentation tends to just write the operation. So this would be a square operation, and then these two get combined in a multiplication operation, and so on. And then the final node, I guess that'd be an addition operation where you add x to 0 to find the final value. So for the purposes of this class, I thought that this notation for the computation graph would be easier for you to understand. But if you look at the TensorFlow documentation, if you look at the computation graphs in the documentation, you see this alternative convention where the nodes are labeled with the operations rather than with the value. But both of these representations represent basically the same computation graph. And there are a lot of things that you can do with just one line of code in programming frameworks. For example, if you don't want to use gradient descent, but instead you want to use the atom optimizer, by changing this line of code, you can very quickly swap in a better optimization algorithm. So all the modern deep learning programming frameworks support things like this and makes it really easy for you to code up even pretty complex neural networks. So I hope this was helpful for giving you a sense of the typical structure of a TensorFlow program. To recap the material from this week, you saw how to systematically organize the hyperparameter search process. We also talked about batch normalization, how you can use that to speed up training of your neural networks. And finally, we talked about programming frameworks for deep learning. There are many great programming frameworks, and we had this last video focusing on TensorFlow. With that, I hope you enjoyed